Welcome to this crash course on external memory. My name is Dustin Smith, and this is my assignment number 5 for CS 301 at the University of Regina. Today, we'll be covering a brief history on external memory before diving deep into flash memory, and in particular its use in solid-state disks as NAND Flash. Before the need for encryption, decryption, and other transfers of messages, most artificial memory was written by people on paper notes or other mechanical processes. A vast array of innovations were introduced between 1940 and 1970 that bridged the gap between the purely mechanical memory and what we know today as digital memory. Although this is an incomplete list, some notable mentions include magnetic core memory, IBM's magnetic tape, whirlwind core memory, the Atlas computer, Signetic's 8-bit RAM that was to be used in their mainframe computer, the hand-woven rope memory, which was weaved by hand as a read-only program used in the Apollo space mission, and Intel's 1103 memory chip, which finally pushed the digital era forward. A little bit more recent, we arrive at hardware of which is more tangible today. Cassettes, CDs, ROM cartridges, SCSI drives, and Blu-rays have all developed through their lifespan, and most have been superseded by some technology or another. This leads me to talk about flash memory, which is used in a number of applications, such as USB drives, solid-state disks, SD cards for cameras, cell phones, and much more. Flash memory, notably, has a few benefits over some other technologies that could possibly serve the same purpose. It's a happy medium between EEPROM and EEPROM memory technologies. Although it was once considered a read-mostly technology, I would argue its uses are more widespread than this. It also features a unique method of erasure wherein the charge stored in the memory cells get flashed with voltage and run to ground to zero out any bits that are stored in the memory cells. This flashing method is where the memory gets its name, and in general is a reliable method for erasing before rewriting. But it comes with some drawbacks. We'll get to those later. NAND flash, in particular, is what is most often used in solid-state disks. It boasts a significant read-write improvement over traditional mechanical disks, and is purely electronic and non-volatile. NAND flash cells look something like this, where bits are stored as either positive or negative charges. These exist above both a silicon layer and an oxide layer. Without getting into the chemistry, we can see there are charges being held by a dielectric barrier. When a high voltage is passed through this layer in the dark gray, we flash the cell and it is erased, with the bits flowing out. Otherwise, the cells will store the charge indefinitely. With newer advents in technology, flash memory manufacturers have found a way to stick as many of these cells into form factors we're familiar with as possible. One approach has been to add a control bit line in and add as many of these cells in stacks. This is what is referred to as 3D NAND because they are literally built vertically. Earlier I showed you a 3-bit memory cell. This is actually just one of a few different standards of flash memory that exist. The 3 bits in NAND flash are a relatively new invention, and for the longest time, just a single bit was used in flash memory storage cells. There are pros and cons to having multiple bits in each memory cell. Each time a cell is flashed, that ferroelectric film that holds the charges degrades a little bit. This means that it can less consistently hold its charges, and after some time will degrade and become unreliable. This means that flash memory has a sort of hard-coded end of life, usually in the hundreds to thousands of read-write cycles, but this varies wildly by technology. SLC, for example, is the most reliable, but because only one bit is stored in memory, it is the most costly to produce a drive of similar capacity. MLC with 2 bits is less costly to produce and still fairly reliable. This trend of cost cuts paired with reliability losses continues with TLC and QLC. The sheer reliability and speed of SLC level chips have led to the heavy adoption of these drives in the enterprise and data center space. As I mentioned previously, the architecture that makes up the NAND flash has a huge impact on its read and write speeds. As a general rule, the less bits that a cell needs to store will mean it can be written to and read from more quickly. Manufacturers in the last few years have taken advantage of this fact, with most consumer SSDs employing a DRAM cache, and some going as far as employing an SLC level cache baked into the SSD whilst filling the rest with TLC memory cells. Thank you for listening to this crash course.